And we're back. So where we ended off last time is I made this claim in the red box. If r is small and t is short, you can use whichever is easiest. Let's give a couple of quick examples. Our first example is if r is 1%, 0.01, and t is 1 year, then 1 plus r equals 1.01, and e to the rt is e to the 0.01, and that equals 1.01005. So the difference between those two is obviously 0.00005. What if r were 1% and t was 10 years? Then 1 plus r to the t is going to be 1.1046, and e to the rt is going to be, r is 1%, t is 10 years, so that's going to be e to the 0.1, and that is 1.1050. So that difference is 0.0004. And now let's take a larger growth rate and a longer period of time. And if r were 3% per year and t were 50 years, then 1 plus r to the t is going to be 4.3839. So the population is going to grow a little bit more than 4 1/3 times what its original population was. At 3% per year for 50 years, it'd be 4 1/3 times bigger. E to the RT, if it were an exponential model, it would be 4.4817 times bigger. So that difference, let's see, 4.3839 divided by 4.4817 is, I think, 97.8%. This thing is 97.8% of e to the RT. And so that difference is 2.2%. So even if the growth rate is 3% per year, which is pretty high for a human population, and the time period was 50 years long, we're still 97.8% of the way. These two models are very close. They're only different by 2.2%. So those are my examples. We can do something a little more detailed later on. But that gives you an idea of how close the geometric and exponential models really are. Okay. Here's something I didn't do last time. Last time, what I showed you was that if we had a model that said kt equals k0, 1 plus r to the t, that was our geometric. I'm going to point out one more time, as I think I did this last time. I'm going to say in both cases that looks like a to the t. If a equals 1 plus r, then we have geometric, our geometric growth model. If a equaled e to the r, then that was the exponential model, the exponential growth model. And I think last time I showed that for the geometric model, we had kt equals k0, 1 plus r to the t. So kt divided by k0 equals 1 plus r to the t. So the teeth root of this kt, of this ratio, 1 over t is the teeth root, that it should equal 1 plus r. So in the geometric growth model, r, I'm just going to write down geometric here. That's the average growth rate in the geometric model. is going to be the teeth root of kt divided by k0. So we want the teeth root of that 1 over t minus 1. That looks like a, let's make that look like a 1 over t. Let's do the same thing for the exponential model. We have, in that case, kt equals k0 e to the rt. We'll do the same thing that we did before. We'll say that kt, the ratio of kt to k0 equals e to the rt. How do we solve for r? What we can do is take the logarithm base e of both sides. So we're going to take the logarithm base e of the ratio kt over k0, and that's going to be r times t. And if that's the case, then the r, the exponential, using the exponential model, the average growth rate r, is going to be 1 over t times the exponential base, the logarithm base e of the ratio kt to k0. So this happens so frequently that I actually don't write log base e. This is, I'm just going to write down the log. And whenever I write down log, I actually mean the log base e. In some cases, this is known as the natural log. Because taking the logarithm to the base e is the natural thing to do. That's the natural log. On some calculators, that is the ln function. I'm just going to write down log, unless I write down something like the log base 10 or the log base 2 or the log, unless I specify the log, I'm always going to mean log base e. So now we have a formula for each of these things. We have one for the geometric growth. I think I'm going to circle this. I'm going to put this in a red box. And I think I'm going to put this one in a red box. So we have a way to solve for the average growth rate for both the geometric and for the exponential growth models. Let me point out something interesting about, I think it's interesting. I'm going to point out something whether or not it's interesting. I'm going to say that in the exponential model, we have r, the exponential model, is 1 over t, the log of kt over k0. As I said before, I'm only going to write log. If I only write log, I always mean the log base e. I'm going to rewrite this in a slightly different way. It's equivalent. I'm going to write now, you may recall that the log of the ratio of things is the difference in the log. So the log of the ratio of kt divided by k0 is going to be the difference between the log of kt and the log k0. I'm going to write that like this. That means the log of kt minus the log of k0. And this whole thing went over 1 over t. How did I get that t? Those were the t years. That was the t. That was the difference between our starting population at time 0, our initial one, at time, that's why k0, and then kt. So that's actually, I'm going to write that one. And now if you take a look at that, you say, that looks like the difference in something divided by the difference in something. And if we are going to look at that, let's draw a quick picture. And here we have time, and here we have time 0, and here we have time t, and here we have the population at time 0. That's going to be k over here. So this is k 0 there, and this is the population at time t. That's k t right there. What this is, here is going to be k0, here is kt, here is 0, and here is t. And so what we have, if we took a look at the line that connects these two, this distance here, what is that distance? That's terrible. Let's draw that a little better. That distance is, oh, I'm sorry. I meant to say that this is the log of kt. So do this on the log scale. If that's the case, there's our log. Then this is going to be log kt minus the log of k0. And this is going to be t minus, this thing is going to be the slope. This is going to be the slope of the populations, slope of k on the log scale. Time is straight, but the population we put on a log scale. Now, let's do this so you understand one more time. If we had exactly the same graph on time, and here is 0 and here is t, it goes like this. We saw that this was what exponential growth looks like. Here is k0, here is kt. Exponential growth is curved, but when we plot it on the log k, so this is just k, and here's the log k. When we plot it on a log scale, then it looks like a slope. And so we have a good diagnostic. So we have a diagnostic rule. If you plot population over time, I'm going to say if you plot the log of population, so if you plot the log of the population over time, and you find the plot looks linear, then the population is growing exponentially. And the slope is the average growth rate R.